Okay, we have mentioned error vector module impairments before, and now it's time to start discussing the more classical impairments at RF frequencies, narrowband technologies. So what we specify as narrowband considerations, of course, they also apply to wideband, but wideband has a more specific impairments. So I will talk about noise, both thermal and phase noise impairments. Talk about spurs. Later on we will mention intermodulations, linearity, EVM impairments, phase linearity, especially in baseband filters, DC offset and LO leakage effects, and IQ, both amplitude and phase impairments. Thermal noise is the first impairment that we will mention. Thermal noise appears in all systems, and it's a known impairment. We have talked about noise figure before. Of course, the representation in EVM of noise figure is also evident, as the thermal noise will create fluctuations around symbol amplitude, but also it will add noise that is fluctuating around the symbol's phase. Both these fluctuations in phase and amplitude created by thermal noise are normally distributed, and of course they create some cloud around of uncertainty around the ideal subsymbol. Phase noise will have mostly effects on the phase of the subsymbol. Phase noise actually reflects random fluctuations in the symbol's or subsymbol phase, and in the constellation map it will translate to changes or fluctuations or noise in the subsymbol phase. So both thermal and phase noise create a cloud of uncertainty in the subsymbol, both amplitude and phase, and it is an uncertainty that is stochastic, so we cannot predistort the signal in some way or calibrate it later on. What we could do when we measure and we want to reduce this uncertainty is average. So we can take the measurement a couple of times, many times, and make an average that will reduce the uncertainty. However, when we do that, it will lengthen the EVM test time. So that's a trade-off, but that's the only thing we can do when we want to reduce the contribution of phase and the thermal noise in test or in the system. Of course, the best approach will be to limit these both noises to required level as early as possible, rather than trying to average later on. Okay, let's move to the effect of a spurious signal in the on the subsymbol information. So here we can see in time domain In red, we can see an ideal sign that may represent a subsymbol. And also in blue, we can see another frequency that can represent a spurious signal that leaked or coupled to the transmitter or the receiver. Can be a clock or another signal that is leaking. And actually, if we add these two signals in time domain, we can see that it creates both amplitude and phase errors that are periodic, and deeper review of these periodic fluctuations in phase and amplitude reveal actually that the spore creates a circle around the ideal constellation point, where this circle has the radius of the spore level. Okay, and of course this can happen to any subsymbol. So in the constellation map, we can see the impairment of a spore as circles with the radius of the spore around the ideal constellation points. If we talk about nonlinearity, and we mentioned before the interference that the different subcarriers can create for their neighboring subcarriers. So nonlinearity is probably a major concern when we talk about impairments and EVM degradation. And we can look at an example of 4 subcarriers that are very nicely spaced, so they are orthogonal, and we can assume that they don't impair each other because they are orthogonal. It's very nice. However, when we introduce these 4 subcarriers into a non-linear device, such as a mixer or even a input LNA, or if we in the transmit channel we introduce these subcarriers to the PA that has finite linearity, then basically the non-linearity, as we can see here, of the device can be described as Taylor expansion of the output current, and we can see that this polynomial has nonlinear terms, like the cubic term, the square term, and the higher terms. And if we look at the baseband signals, then the square term of the polynomial can generate frequencies that actually fall on top of the original subcarriers and actually impair the amplitude and may also impair the phase of these. And in RF frequencies, the cubic term will contribute new products that are the result of multiplication of the original product that will fall on top of the original product. So this is very similar to the two-tone IP3 test that people used to perform and still do on certain circuits. But two tones will create other tones when they are introduced to a nonlinear circuit, And these two tones can still be within band because we have multiple carriers. So every couple, every three, every combination of frequencies that we can think of may create impairment frequencies that are in band. Okay, and it's very easy to show it through simple trigonometric exercises of multiplication. However, the simplicity of explaining this is not very helpful when we try to avoid these issues of nonlinearity, because they are very important and strong impairment in the total EVM impairment. We mentioned peak to average before. Yeah, it's a very known impairment in modern communication. Yes, there are ways to pre-distort the modulation in a way that will reconstruct the original linear output. However, it is requiring an effort that is substantial. And the more we crowd these subcarriers, and the more we increase data rate and go to higher modulation scheme like 64 QAM, 256 QAM, the higher these problems or the more severe these problems of linearity become. And again, the best way will be to make the circuitry more linear. However, there's always a trade-off with power efficiency, current consumption, and we have to deal in communication systems with this nonlinearity also when we do the signal processing, as mentioned. We cannot have very linear circuitry that will support no consideration of nonlinear behavior. Another way to look at nonlinearity is to take these four subcarriers and look at them in time domain. So now we have different signs, four signs, each with a different amplitude and phase that can represent different symbols, different subsymbols. And if we add them in time domain, we can see the sum in black. And actually, it is very obvious that we have peaks and we have lower instances where these where the sum is very low in amplitude, and we can visually see the peak to average problem that was mentioned before. Of course, to include all the symbol information, we must transmit the peaks without any clipping, without any way of shaping them. Okay, and again, if we try to do that, we have to design very linear circuitry. And many times, or most of the times, it will be a trade-off with the power consumption, because there will be instances where the information or the total signal transmitted is very low in amplitude, but we still draw current from the circuitry. Okay. So after covering noise and linearity, we can and spores, we can talk about filtering in baseband usually, and the amplitude effect on the error vector magnitude. We use filters in baseband to define the RF bandwidths of interest, and to reject blockers in the receive mode. In transmit mode, we usually want to reject the alias. So baseband filters are employed both in transmit and receive chains, and because they're usually the narrowest filters in the chain, they are of highest interest in the chain. If we look at the amplitude of both Chebyshev or Butterworth examples, we can easily note that both these different filters introduce different amplitudes and different frequencies. Okay? In a different way. Every different filter will have a different transfer function, but it is clear that from the shape that we see, that the Chebyshev will have some ripple, a Butterworth will have more smooth shape, but the amplitude in lower frequencies will be a little bit higher than the amplitude closer to the band edge, and so different subcarriers will get different gain, which of course impair the original information carried by the respective subsymbol. So this is an impairment that can be recorded, tested, and then later on compensated for or offset. Okay, we can learn the shapes of these filters, and in the digital domain we can give each subcarrier a different weight in a way that will reflect compensation for such effects. Filters also have phase performance that is critical, because we would like the phase over bandwidths to change linearly. And if we look at the transfer function of a filter, it has an amplitude part and it has a phase part. And if we look at the phase part, we usually prefer to look at the derivative of the phase over omega, over the radial frequency, and to talk about group delay. And it is very well known that we expect the group delay to be a constant over bandwidths. However, amplitude and phase transfer functions are related, and so at the band edge where the amplitude is changing in all filters, also the group delay is changing, and it is not constant anymore. So this change in the group delay also create changes in the subsymbol phase, and subsymbols that are closer to DC or in lower frequencies will have linear phase, while subsymbols that are closer to the band edge will have some phase offset. As we did with amplitudes, we can do a similar learning of this impairment in testing, and then compensate for it. And in digital domain, we can offset these phase errors created by a group delay at the bend edge. Okay, we can now talk about DC offset and LO leakage effect on EVM. So if we talk about different DC levels for I and Q, it can be described in the constellation map as a shift of the origin to a different point than the original origin, depending on the DC offset that that exists in the different I and Q channel. So it can be a DC offset only in I, only in Q, or in both. And again, in the constellation map, it will create a constant error depending on the I and Q DC offset from the original subsymbols. So all these subsymbols will be shifted from their original place in the same error vector, and this can be studied and cancelled later on. Same goes for the LO leakage, because the LO leakage actually, if we do the full transmit receive loop, translates to DC offset. So it's an equivalent problem, and it can also be learned and compensated in the baseband processor. Okay, now we will cover IQ mismatch impairment and the effect on EVM. So when we talk about I and Q mismatch, we have two errors that we can consider. One of them is the amplitude error, and the other one is the phase error. When we talk about amplitude error, we talk about I and Q channels being amplified with a slightly different transfer function, or with a slightly different gain, for example. And so if we have a slightly different gain on I and Q, the original subsymbol will be shifted in a way that will reflect this difference in gain. And of course, this creates an error that will need to be studied and then compensated in baseband or digital processing. And as we mentioned before, there may be a shift also in the theoretically 90-degree phase difference of the I and Q symbols. So we generate the constellation plan by orthogonal I and Q amplitudes. However, due to different transfer functions or other impairments, these two axes may be not exactly 90 degrees relative to each other, but a different phase that is not exactly 90 degrees. And this different phase will also translate into an impairment in the location of the ideal subsymbol. And again, we can learn this and try to compensate for it in processing. Of course, the best thing is not to have all these impairments, but to a certain degree, we will always have to deal with them. It's impossible to build a transmitter or receiver that is wideband to include many subsymbols over a wide bandwidth, and maintain the exact 90 degrees between I and Q all over the bandwidth. So we will have to deal with some inaccuracies and then to compensate them.